The word comes from the Greek. Historically, heliocentrism was opposed to geocentrism, which placed the Earth at the center. The notion that the Earth revolves around the Sun had been proposed as early as the 3rd century BC by Aristarchus of Samos. But at least in the post-ancient world, Aristarchus's heliocentrism attracted little attention, possibly because of the loss of scientific works of the Hellenistic era. It was not until the 16th century that a geometric mathematical model of a heliocentric system was presented by the Renaissance mathematician, astronomer, and Catholic cleric Nicolaus Copernicus, leading to the Copernican revolution. In the following century, Johannes Kepler elaborated upon and expanded this model to include elliptical orbits, and Galileo Galilei presented supporting observations made using a telescope. With the observations of William Herschel, Friedrich Bessel, and others, astronomers realized that the Sun was not the center of the universe as heliocentrists at the time of Copernicus had supposed. Modern thinking is that there is no specific location that is the center of the universe, per Albert Einstein's principle of relativity. Early developments. To anyone who stands and looks up at the sky, it seems that the Earth stays in one place, while everything in the sky rises in the east and sets in the west once a day. However, with more scrutiny one will observe more complicated movements. The positions at which the Sun and Moon rise change over the course of a year. Some planets and stars do not appear at all for many months, and planets sometimes appear to have moved in the reverse direction for a while, relative to the background stars. As these motions became better understood, more elaborate descriptions were required, the most famous of which was the geocentric Ptolemaic system, which achieved its full expression in the 2nd century. The Ptolemaic system was a sophisticated astronomical system that managed to calculate the positions for the planets to a fair degree of accuracy. Ptolemy himself, in his Almagest, points out that any model for describing the motions of the planets is merely a mathematical device, and since there is no actual way to know which is true, the simplest model that gets the right numbers should be used. However, he rejected the idea of a spinning Earth as absurd, as he believed it would create huge winds. His planetary hypotheses were sufficiently real that the distances of Moon, Sun, planets and stars could be determined by treating orbit celestial spheres as contiguous realities. This made the star's distance less than 20 astronomical units, a regression. Since Aristarchus of Samos's heliocentric scheme had centuries earlier necessarily placed the stars at least 2 orders of magnitude more distant. Greek and Hellenistic world Pythagoreans. The non-geocentric model of the universe was proposed by the Pythagorean philosopher Philolaus. This system postulated the existence of a counter-Earth collinear with the Earth and central fire, with the same period of revolution around the central fire as the Earth. The Sun revolved around the central fire once a year, and the stars were stationary. The Earth maintained the same hidden face towards the central fire, rendering both it and their counter-Earth invisible from Earth. The Pythagorean concept of uniform circular motion remained unchallenged for approximately the next 2,000 years, and it was to the Pythagoreans that Copernicus referred to show that the notion of a moving Earth was neither new nor revolutionary. Kepler gave an alternative explanation of the Pythagoreans' central fire as the Sun, as most sects purposely hid their teachings. Heraclides of Pontus said that the rotation of the Earth explained the apparent daily motion of the celestial sphere. It used to be thought that he believed Mercury and Venus to revolve around the Sun, which in turn revolves around the Earth. Macrobius Ambrosius Theodosius later described this as the Egyptian system, stating that it did not escape the skill of the Egyptians, though there is no other evidence it was known in ancient Egypt. Aristarchus of Samos, the first person known to have proposed a heliocentric system, however, was Aristarchus of Samos. Like Eratosthenes, Aristarchus calculated the size of the Earth, and measured the size and distance of the Moon and Sun, in a treatise which has survived. From his estimates, he concluded that the Sun was 6 to 7 times wider than the Earth and thus hundreds of times more voluminous. His writings on the heliocentric system are lost, but some information is known from surviving descriptions and critical commentary by his contemporaries, such as Archimedes. Some have suggested that his calculation of the relative size of the Earth and Sun led Aristarchus to conclude that it made more sense for the Earth to be moving than for the huge Sun to be moving around it, though the original text has been lost. A reference in Archimedes' book The Sand Reckoner describes another work by Aristarchus in which he advanced an alternative hypothesis of the heliocentric model. Archimedes wrote, "You King Gelonor, where the universe is the name given by most astronomers to the sphere, the center of which is the center of the Earth, while its radius is equal to the straight line between the center of the Sun and the center of the Earth. This is the common account as you have heard from astronomers." But Aristarchus has brought out a book consisting of certain hypotheses, wherein it appears, as a consequence of the assumptions made, that the universe is many times greater than the universe just mentioned. His hypotheses are that the fixed stars and the Sun remain unmoved, that the Earth revolves about the Sun on the circumference of a circle, the Sun lying in the middle of the orbit, and that the sphere of fixed stars, situated about the same center as the Sun, is so great that the circle in which he supposes the Earth to revolve bears such a proportion to the distance of the fixed stars as the center of the sphere bears to its surface. Aristarchus believed the stars to be very far away, and saw this as the reason why there was no visible parallax, that is, an observed movement of the stars relative to each other as the Earth moved around the Sun. The stars are in fact much farther away than the distance that was generally assumed in ancient times, which is why stellar parallax is only detectable with telescopes. Archimedes says that Aristarchus made the star's distance larger, suggesting that he was answering the natural objection that heliocentrism requires stellar parallactic oscillations. He apparently agreed to the point but placed the stars so distant as to make the parallactic motion invisibly minuscule. Thus heliocentrism opened the way for realization that the universe was larger than the geocentrists taught. Seleucus of Seleucia. Since Plutarch mentions the followers of Aristarchus in passing, it is likely that there were other astronomers in the classical period who also espoused heliocentrism, but whose work was lost. The only other astronomer from antiquity known by name who is known to have supported Aristarchus' heliocentric model was Seleucus of Seleucia, a Hellenistic astronomer who flourished a century after Aristarchus in the Seleucid Empire. Seleucus adopted the heliocentric system of Aristarchus and is said to have proved the heliocentric theory. According to Bartholindert van der Weyden, Seleucus may have proved the heliocentric theory by determining the constants of a geometric model for the heliocentric theory and by developing methods to compute planetary positions using this model. He may have used early trigonometric methods that were available in his time, as he was a contemporary of Hipparchus. A fragment of a work by Seleucus has survived in Arabic translation, which was referred to by Rhazes. Alternatively, his explanation may have involved the phenomenon of tides, which he supposedly theorized to be caused by the attraction to the Moon and by the revolution of the Earth around the Earth-Moon center of mass. Medieval Europe. There were occasional speculations about heliocentrism in Europe before Copernicus. In Roman Carthage, the pagan Martianus Capella expressed the opinion that the planets Venus and Mercury did not go about the Earth, but instead circled the Sun. Capella's model was discussed in the early Middle Ages by various anonymous 9th-century commentators, and Copernicus mentions him as an influence on his own work. During the late Middle Ages, Bishop Nicole Orsma discussed the possibility that the Earth rotated on its axis. while Cardinal Nicholas of Cusa in his learned ignorance asked whether there was any reason to assert that the sun was the center of the universe. In parallel to a mystical definition of God, Cusa wrote that, thus the fabric of the world will quasi have its center everywhere and circumference nowhere. India Aryabhata, in his magnum opus Aryabhatiya, propounded a planetary model in which the Earth was taken to be spinning on its axis and the periods of the planets were given with respect to the Sun. He accurately calculated many astronomical constants, such as the periods of the planets, times of the solar and lunar eclipses, and the instantaneous motion of the Moon. Early followers of Aryabhata's model included Varahamihira, Brahmagupta, and Bhaskara II. Nilakantha Somayaji, in his Aryabhatiyabhasya, a commentary on Aryabhata's Aryabhatiya, developed a computational system for a partially heliocentric planetary model, in which the planets orbit the Sun, which in turn orbits the Earth. Similar to the Tychonic system later proposed by Tycho Brahe in the late 16th century. In the Tantra Sangraha, he further revised his planetary system, which was mathematically more accurate at predicting the heliocentric orbits of the interior planets than both the Tychonic and Copernican models, but like Indian astronomy in general fell short of proposing models of the universe. Nilakantha's planetary system also incorporated the Earth's rotation on its axis. Most astronomers of the Kerala school of astronomy and mathematics seem to have accepted his planetary model. Medieval Islamic world Muslim astronomers generally accepted the Ptolemaic system and the geocentric model, but by the 10th century texts appeared regularly whose subject matter was doubts concerning Ptolemy. Several Muslim scholars questioned the Earth's apparent immobility and centrality within the universe. Some accepted that the Earth rotates around its axis, such as the 10th century astronomer Abu Sa'id al-Sijzi. According to al-Biruni, Sijzi invented an astrolabe called al-Zuraki based on a belief held by some of his contemporaries, that the motion we see is due to the Earth's movement and not to that of the sky. The prevalence of this view is further confirmed by a reference from the 13th century which states, according to the geometers, or engineers, the Earth is in constant circular motion, and what appears to be the motion of the heavens is actually due to the motion of the Earth and not the stars. Early in the 11th century Al-Hasan wrote a scathing critique of Ptolemy's model in his Doubts on Ptolemy, which some have interpreted to imply he was criticizing Ptolemy's geocentrism, but most agree that he was actually criticizing the details of Ptolemy's model rather than his geocentrism. By the end of the 12th century, some Islamic astronomers developed complete alternatives to the Ptolemaic system, such as Nur ad-Din al-Bisruji, who considered the Ptolemaic model as totally not real. Abu Rayhan Biruni discussed the possibility of whether the Earth rotated about its own axis and around the Sun, but in his Masudic canon, he set forth the principles that the Earth is at the center of the universe and that it has no motion of its own. He was aware that if the Earth rotated on its axis, this would be consistent with his astronomical parameters, but he considered this a problem of natural philosophy rather than mathematics. Qutb al-Din Shirazi also discussed the possibility of heliocentrism, but rejected it. At the Maraha and Samarkand observatories, the Earth's rotation was discussed by al-Khatibi, Tusi and Cuja. The arguments and evidence used by Tusi and Cuja resemble those used by Copernicus to support the Earth's motion. However, it remains a fact that the Maraha school never made the big leap to heliocentrism. Some historians maintain that the thought of the Maraha school influenced Copernicus. In particular, the mathematical devices known as the Urdi lemma and the Tusi couple. Copernicus used such devices in the same planetary models as found in Arabic sources. Furthermore, the exact replacement of the equant by two epicycles used by Copernicus in the Commentariolus was found in an earlier work by Ibn al-Shatai of Damascus. Ibn al-Shatir's lunar and Mercury models are also identical to those of Copernicus. However, this remains speculative as no researcher has yet proven that Copernicus knew about Ibn al-Shatir's work or the Maraha school. It has been argued that Copernicus could have independently discovered the 2Z couple or took the idea from Proclus's commentary on the first book of Euclid, who Copernicus cited. Another possible source for Copernicus's knowledge of this mathematical device is the Questiones de Spera of Nicole Orsma, who described how a reciprocating linear motion of a celestial body could be produced by a combination of circular motions similar to those proposed by Althusser. A recent study adds further proof that there is actually very little evidence that Copernicus knew or was influenced by the Maraha or other, late Islamic astronomical schools. Nevertheless, Copernicus mentions some of the early Islamic astronomers whose theories and observations he used in the revolution of this, namely al-Battani, Thabit ibn Qurra, al-Zarqali, ibn Rushdi, and al-Bisruji.